Hi, chemistry students. This is going to be the second notes presentation video that you guys listen to for me. Before we get started, once again, I'm going to make sure we're all on the same page as I go through this. You should be over here on this document filling in blanks as we go. So really quickly, I want to just briefly talk about our learning intentions and our success criteria. By the end of this, you should know how to perform successful mathematical operations. You should be able to use scientific notation to express numbers of extreme magnitude. You should be able to explain the difference between accuracy and precision, and use significant figures rules to determine levels of accuracy. So first, I just want to go ahead and talk about what scientific notation even is. It is another way to write really, really big or really, really small numbers. I sometimes like to call it the cheater method, because if you're looking at this really, really, really big number, this is a ridiculous number to have to write out longhand all of the time if you're using it in whatever calculations. So another way to write this number is down here, 6.02 times 10 to the 23rd power. These two numbers are the same. They don't look the same, but they are, and I can show you why they are, actually. So let me just demonstrate really quickly. You know that this number right here, this really big number, has an implied decimal point right there. You would have known that without me having to tell you, because you've all seen a number before. This number down here has a decimal place between the 6 and the 0. So to get the decimal place from here to there, we have to move it a certain number of spaces. So if you take it and you move it to the left, 3, 6, 9, 12, 15, 18, 21, 22, 23 spaces over to the left, notice that I moved it 23 spaces and that exponent is 23. Suddenly you get 6.02 with a bunch of lagging zeros that you don't have to write. But 6.02 and this number by itself is not the same thing. So to make sure that you know you're talking about the same number, you have to multiply 6.02 by 10 to the power of something. Since we moved that decimal place over 23 spaces, your exponent becomes 23. So that becomes very easy to write big, big numbers in scientific notation so that you don't have to keep track of all of these zeros. Okay? So let me just go ahead and erase all these blue drawings that I just did, and we'll move on. So to move between standard form and scientific notation form, there's a couple of things that you should be aware of. One is that if your exponent is positive, like this number is right here, to move from scientific notation to standard, you're going to move that decimal place to the right if your exponent is positive. And to demonstrate that, you're 1.34, you take this decimal place, you move it over 1, 2, 3, 4. You fill in zeros into your empty spaces, suddenly you have this number. However, if you have a negative exponent, you're going to do the opposite thing. You're going to take your negative exponent, you're going to take your decimal place, and you're going to move it to the left. Okay, so you have your 5.12. You're going to take this decimal place and go 1, 2 spaces to the left and fill in your 0. You know it's a 2 because your exponent is a -2. And now, suddenly, you have 0.0512. You have this number right here. Okay, so at this point in your notes, you should have some blanks in this next space, and I'd like you to pause the video at this point, and I'd like you to try those on your own. When I see you in class, I will go over what the answers to those questions are. Okay, so next, you could do the opposite thing. you could go from standard form and want to put that number in scientific notation. So essentially, you're going to do the opposite thing that I just showed you how to do. You know there's an implied decimal right there, and you are going to move that decimal to create a number in scientific notation. Now, the rules for how to do that, you want this number to be somewhere between 1 and 9.9. I don't want to see some answer like 376.3 times 10 to the whatever. No, you want one number followed by a decimal point followed by another number times 10 to the some exponent. That is the form we are looking for. So if you have 67,000 and you have your implied decimal place, we're going to take that decimal place and go 1, 2, 3, 4. Now we have one number, a decimal point, one number. And then now that you've moved it over 4 spaces, this time to the left because you're going from standard form into scientific notation, you're going to end up with 6.7 times 10 to the 4th. Okay, with this one, you're going to take this decimal place, you're going to go 1, 2, 3, 4, 5. You end up with 3.1 times 10 to the negative 5th. A good rule of thumb for moving from standard into scientific notation is if you're starting with a big number, this exponent should be positive. If you're starting with a tiny number, this exponent should be negative. And that is specifically for moving from standard form into scientific notation. Once again, there should be some, hey, now you try some problems in your notes. I would like you to try them on your own. And when we get to class, I will tell you what the answers are. Now, there are going to be some rules because you're not only going to have to be able to navigate between standard form and scientific notation, you're going to have to be able to add and subtract those numbers as well. Now, you need to be able to effectively add and subtract numbers. You need the exponent to be the same because you may not add 3.3 times 10 to the 3rd plus 3.7 times 10 to the 8th. You may not easily add those numbers together because the real form of those numbers is what? 3300 plus 37, 1, 2, 3, 4, 5, 6, 7, I believe. Because that would be the two numbers you're actually adding. You wouldn't actually be adding the 3.3 plus 3.7. That's not how that works. So always, 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 if you are going to add things in scientific notation, they have to have the same exact exponent. Never, ever forget that. But once they do have the same exponent, it becomes super easy. All you have to do is the 3.3 plus the 2.1, and then it's the same exponent, so you end up with the 5.4 times 10 to the 3rd. There's a couple of different ways that you can manipulate your numbers if you do have numbers with different exponents, and I'll explain more about that. So if they're not the same, you're going to have to change them to be the same. So manipulating numbers in scientific notation isn't actually that bad. You just have to adjust your exponent and adjust your decimal point accordingly. So if I was trying to subtract 2.0 times 10 to the 3rd from 7.1 times 10 to the 4th, you're going to want to change one of these things somehow. You could either change this number to be times 10 to the 4th, or you could change this number to be times 10 to the 3rd. It doesn't really matter which one you do, you just need that same exponent. So 7.1 times 10 to the 4th could also be 71 times 10 to the 3rd. Or you could say 2.0 times 10 to the 3rd could become 0.2 times 10 to the 4th. But again, you just kind of have to pick what it is that you're doing. For multiplying and dividing, on the other hand, actually, Multiplying and dividing is a lot easier, in my opinion, than adding and subtracting because you don't have to mess with changing something around to the same exponent. All that you have to do is say, okay, well, I'm going to multiply my two numbers, my 3.0 and my 2.0, and then I'm going to add the exponents together. So this 3 times 2 is 6 times 10 to the 3 plus 4 is 7, and that's your answer. For dividing, you do the exact opposite. You have 9 divided by 3. Well, that's 3. 5 minus 2 is 3. So you end up as your answer with 3.0 times 10 to the third. So like I said, multiplying, dividing is actually a little bit easier, and I like doing that much, much better than I do adding and subtracting. So moving on to significant figures. This is going to become very important when we round things off, and it's also going to be very important so that you know how many decimal places to round to in your answer. The reason that we do this is because any measurement that's ever taken in science is an approximation to a certain amount of decimal places. So I can put a cube in front of you and tell you that that cube weighs 1 gram. But in reality, I put it on a scale and I measured to see if it was 1 gram. And on that scale, it came out to 1 gram. But I don't know necessarily, depending on what scale I use, I know it could be 1.00 grams. But anything after that is unknown, if that's how accurate my scale is. If I have a really good scale, I could know that it's 1.000000 grams. But then again, any decimal place after that would remain unknown. So depending on how good your measuring equipment is, you could be really accurate or not at all accurate. Like your household scales, when you step on and it tells you you weigh X amount of pounds, that's only accurate to maybe 1/10 of a pound if you're lucky. Some scales are only accurate to the nearest couple of pounds. It, again, depends on your scale. So, one thing that's important to understand is the difference between accuracy and precision. You can think of accuracy as being right, being correct, hitting a target correctly. So that's what this graphic is trying to explain to you. If you're precise, but you're not accurate, it means all your data was super close together, but it's not necessarily right. So those two things are important to understand the difference between. So let's try an example really quickly. Let's just see. Let's say that you want to haul a bunch of heavy stuff up to the top floor of a building, but the elevator has a max capacity of, let's arguably say, 1,000 pounds. Obviously, this image doesn't match that, but let's say it can only haul 1,000 pounds. But you have a lot of stuff, and you know it's pretty heavy, and you really don't want to exceed that elevator's max capacity, because if you do that, you might get stuck in it, it might break. That's dangerous. So you're going to use your big scale that you for some reason happen to have, for the sake of this metaphor, to try and weigh your stuff to see if you can bring it all in one trip. And all of your stuff, let's say you want to make sure that it doesn't exceed that 1,000-pound limit plus you, because you also have to go up to the top of the building, right? But your scale is only accurate to the nearest 10 pounds or so. So if you weighed something that you knew was 105 pounds, that scale might read 115 or 100 or 95 or 96 or anything in that space, because it's only accurate to the nearest 10 pounds. That scale kind of sucks. But if that's the scale you're using, then that's what you have. So because you're going to put all of your stuff on there, right? And you are going to determine that scale says that all of your stuff together weighs 995 pounds. Now, plus you. That's under the 1,000-pound limit, right? But your scale's inaccurate, so you don't know if it's actually 995 pounds or if the scale's just reading it wrong, because it's only accurate to that one place. So its true weight could be more than that. But if you had a really accurate scale that, let's say, could tell you that your stuff weighed 995.07 pounds, you would know for a fact, because that scale is more accurate, that you could safely put all of your stuff and get in the elevator and you would be below its max capacity. So that's what sig figs are really for, is to tell you how accurate whatever answer you have is, because it's going to tell you how accurate all of the numbers were in the problem to get you to your answer. So that obscenely long metaphor aside, here's the rules that you have to pay attention to, okay? So first of all, any digit that's not 0 is going to be a significant digit if you're looking at a number. So for example, this 1.23 has 3 significant figures in it, or 3 significant digits, because you have this one right here, 2 and 3, 3 significant figures. Another rule, or sorry, there's another example. This one would have 4 significant figures because there's 4 non-zero digits there. Any zeros that happen to be between a non-zero digit is also going to be significant. So for example, here, 1205 or 1205, that has 4 significant figures because even though there's a 0, it's between non-zeros. So we have 1, 2, 3, and 4, okay? This one has 5 significant figures, 1, 2, 3, 4, 5. Let me go ahead and erase all that. Any placeholder digits are not significant. What I mean by placeholders are these guys right here. See these 3 zeros? Those are placeholder zeros. They do not need to have any significance attached to them whatsoever. These zeros that precede the 2 here, this 0, this 0, this 0, this 0, placeholder zeros. They are not significant. So this number right here would only have 2 significant figures. This number here only has 1 significant figure. However, this number has 5 sig figs because these zeros are between non-zero digits. Any final zeros that happen to be after a decimal point are in fact significant. So this rule kind of seems a little odd probably after this rule up here, but think about this. Think about this in terms of weight. Let's say you had a super sensitive scale that weighed some object to be 1.200 grams. You know that that object weighs 1.200 grams instead of weighing 1.217 grams. That scale has told you that it is accurate to this many decimal places. That's why this significant figure stuff is actually important, and that's why final zeros after a decimal point are in fact important. Okay? So this one is going to have 7 significant figures because it's 1, 2, 3, 4, 5, 6, 7, because you have those final zeros after a decimal point. So let's do a little bit of practice. I'm going to do this with you. This one would have 1, 2, 3, 4 significant figures. This one only has 2 significant figures because there's no decimal point to tell you that these zeros would be significant. This, on the other hand, same exact number, but it has 1, 2, 3, 4, 5, 6, 7 significant figures. This only has 1 significant figure because you have a bunch of placeholder zeros right there, and this one would have 2 significant figures. If you are doing math with sig figs, this is where it gets kind of fun. If you are adding and subtracting 2 numbers, your answer should have the same number of decimal places as the number in the problem that has the least amount of decimal places, which is kind of a mouthful to say, so let me show you an example. For this particular problem, we have 1.12, which has 3 significant figures. We are adding that to 2.3, which has 2 significant figures. Between the two of these numbers, this one is the least amount of significant figures, so you know that your answer should have 2 significant figures in it. So if you add these raw numbers together, if you add 1.12 plus 2.3, you get 3.42. However, I just told you your answer can only have 2 significant figures, so you would have to round this off and essentially get rid of that third number. So this 2 would get rounded off. 0.42 gets rounded to 0.40. So now your answer becomes 3.4 with 2 significant figures. Again, I know it seems very odd to do, and when I show you more examples, it'll feel even more wrong to you, but it is what it is, and you do need to know these rules. If you are multiplying and dividing, the exact same rules apply. You have to have your answer with the same amount of significant figures as whatever number in the problem had the least. So in this example, we have this number which has 3 significant figures, this number which has 2 significant figures, so your answer over here can only have 2 significant figures. If you add if you multiply 3.4 times 1.2, you get 4.08, but you have to round it at that point to a number that only has 2 significant figures. So 4.08 rounds to 4.1, hence this is your final answer. Sorry, let me clear those drawings. This one feels terrible. It feels so awkward to do because 7 times 24 is 168. 7 has 1 significant figure, which means our answer can have 1 significant figure. So you have to round 168 to 200. It's not very accurate, is it? But it is precise to the particular level of significant figures that you have. Once again, I get it. It's weird. I don't like it either. I didn't like it, but it is what you have to do. Here's a couple more examples if you wanted to look at them, and this one even converts your 5,040,000 into a properly rounded answer in scientific notation. So try to do some practice with these. Try to look at these problems and understand how they got there. I will be going over this in class, so worry not.